Thank you very much. So can you hear me? All right. So it's a real pleasure and honor to be here and in beautiful Michigan to celebrate the birthday of one of my heroes. And I can see that to kind of celebrate this centennial, you have invited a lot of luminaries. First and foremost, Abbas El-Gamal, World Authority in Information Theory, 2012, Shannon Award winner. Bob Calderbank, World Authority, 2015, Shannon Award winner. Michel F. Rose, future Shannon Award winner, 2018, 2019, 201X. And then the only thing I'm wondering is what is it that I do here? Clearly, I don't have the authority nor the knowledge to give you a lecture about the great master, even though I have read many of his papers that had a profound influence on my thinking. But being a completely outlier, my talk, of course, has very little to do with the talks you've heard and the ones you'll hear later on today. But I thought I should still give you and say a few things about the great master, Claude Shannon. And so in order to do this, there is a period in time I'm extremely fascinated with, especially when it comes to science, and that the period that goes from roughly 1905 to 1948. And what happens during this period? Well, physics is turned upside down twice. First by relativity, then by quantum mechanics. Mathematics, logic, and I would even argue philosophy is turned upside down by Gödel's incomplete theorem. Economics is turned upside down by the crazy and radical theories of Keynes. Not only this, but we have the birth of many fields as scientific disciplines. We have the birth of computer science as a scientific discipline because of Turing, Church, and von Neumann. We have the birth of my field of statistics as a scientific discipline, something that is worthy of a college degree because of Fisher, Neyman, Pearson, and many other great giants. We have the birth of probability theory as a mathematical discipline because of Kolmogorov. We have the birth of information theory due to Claude Shannon, whom we celebrate today. And I could stop here, but I feel I have to extend the deadline a little bit to include the life sciences, and I would have to conclude with the discovery of the double helix by Crick and Watson. But what's amazing is we have fields being turned upside down. We have new fields being invented, and it's really a golden era of scientific research, this first half of the 20th century. Now, I'm not the only one to recognize this. The Time magazine elected Einstein to be the man of the century, recognizing that the 20th century was the century of science. And at the same time, roughly, lots of magazines played this game. By the way, the runner-up was Gandhi. And Einstein edged Gandhi. The Financial Times elected his, or man or woman of the century. It happens to be a man. And do you know who that is? Johnny von Neumann. Again, emphasizing this, that we live in that the 20th century was about science, especially early 20th century. And I believe that Claude Shannon really belongs to these things. It could equally have been featured by these magazines exactly for the reason that Abbas mentioned earlier, that somehow we live in an information age and it's really because of him. I would also argue that Einstein is great, and as Abbas said, he looms large. I think if Einstein had not devised special relativity, someone else would have. In fact, Poincaré kind of had it. I don't know who would have come up with a mathematical theory of communication. It's, to me, like an extraordinarily singular achievement. Now we have these sort of singular minds, and I think Claude Shannon looms large in this crowd. What I want to emphasize again is that it seems that we've been through a series of intellectual disruptions. There was one disruption after the next. If you can imagine a physicist falling asleep in 1905 and waking up in 1945, then they would not recognize the field. Now, if I do and I compare this with my own lifetime, if a physicist fell asleep in 1975 and wakes up in 2015, yeah, the field has changed a bit, but you would recognize it. Now, it's a bit different, and if I were to ask, that's why I ask my students sometimes in class, name an intellectual breakthrough on par with those of these guys. It's kind of hard. And I would say that it's kind of, at least in the place where I live in, of course we have phenomenal technological achievements, and with these technological achievements comes a form of hubris, for example. And I know I'm a bit controversial here, but in Silicon Valley, there's these ideas that AI, machine learning, you name it, big data, will solve everything, that we don't really need theories anymore, that the answer lies in data analysis, and so on and so forth. And what I want to say is, well, tell me, in this view of the world, how can you imagine these 1948 papers? Like, tell me how you're going to mine an idea like this. It's just impossible. And so...
Those are opinions expressed in this program, or those are presented.
Okay. All right. Okay. These are my views alone. Okay. All right, so that's my tribute. A pure genius. Okay. All right, so now I'm here in Michigan. I think this event is organized by the Center for Data Science, and so I'm going to wear my data science hat for the rest of this talk. All right, so let's start with a bang. This is a cover of The Economist, How Science Goes Wrong. In fact, there are many, many magazines in the country and abroad. The Economist is based in London, obviously, that describe disturbing facts. So if you look at The Economist dated October 2013, you'll have a series of articles explaining that something is terribly wrong with the state of scientific research. All right, and so you see scientific research has changed the world. Now it needs to change itself. We are in the era of unreliable research. There's trouble at the lab. People would say, science used to self-correct, but now it's not self-correcting anymore. I see a train wreck looming, and so on and so forth. And there's reason for concern. So if you actually look at what's inside these articles, you'll find disturbing things. So for example, I'll focus on two disturbing things. Amgen, which is a biotech company based in California, what they did is they did something simple. They took 53 papers that they considered to be absolutely landmark in basic cancer science. And I'm talking stuff published in Nature, Science, and the likes. And they tried to reproduce them. They tried to reproduce the findings and obtain the same claims. Out of 53 studies, they could only replicate 6. 47 effects or discoveries that somehow vanished into the air. Healthcare Bayer, the German equivalent of Amgen, did about the same thing. They took 67 seminal studies. They could reproduce less than a quarter. Now, if you work for the Food and Drug Administration, you're familiar with all of this because, well, I'm not going to go through FDA trials and so on, but basically you know that there's a long process to bring a drug to market, and by the time you reach phase 3, things should be a slam dunk. But what the Food and Drug Administration finds is that 50% of phase 3 trials end up in error, and that this number keeps on rising with time. Right, so there's an enormous concern about this. This is a New Yorker, the truth wears off. Popular press littered with negative things like significance chasing, publication bias. I have a colleague at Stanford, John Ioannidis, who is widely cited in all of these articles, who published an influential paper estimating that roughly 80% of what you'll find published in the life sciences is actually false. New York Times, new truths that only one can see, and it goes on and on. And every week you have a new article about stuff like this. Now, I've been told that the public confidence in science is at an all-time low in the United States. And of course, too many articles of this kind cannot be very helpful. And so there's a great danger in seeing erosion of public confidence in science. And I think really given how well science has served the United States, it would be a very dangerous thing, a dangerous proposition, if scientists were seen as politicians. But the scientific community is taking the problem very seriously and is beginning to respond in ways that I will briefly describe. Okay, so first of all, there is something called the reproducibility initiative, where let's say you run an experiment, you get results that sound too good to be true, you're a bit worried about publishing them because you're worried that they will not reproduce. Well, you can submit your protocol to an exchange, and I give you the address of the website if you're interested in this. And so, of course, against a fee, what this exchange will do is they will try to reproduce your findings before you publish. And sometimes they will do this for a fee, for free. And so it is obviously a step in the right direction. If you look at the top magazines, I give you the example of Nature, but I could talk to you about Science as well. We can be extremely cynical about this, and maybe during lunchtime we will be. But at the moment, let's try to be positive. And so Nature has completely changed its editorial line. They're fully aware that they publish a lot of stuff that does not stand up to close scrutiny. And what they're asking authors now is to share their data, share their code, so that statisticians can actually go through the methods and test the robustness of various claims vis-a-vis model misspecification, parameters, little changes in parameters, and so on. Like, it's a step in the right direction as well. Finally, the president of the National Academy of Science, every year there's a meeting, and the biggest thing on his agenda is this. And he urged the scientific community to respond forcefully to this crisis in reproducibility that we seem to have. All right, so what has changed? Why is it that all of a sudden we're flooded with things that do not reproduce, when in fact, up till a few years ago, things seem to be pretty fine? Well, what has changed is that the way we do science has changed completely. And so to understand this change, I think it's better to go back in time and see how we used to do science. And science has followed what we might want to call a Popperian logic, formalized by a great British philosopher, Karl Popper, which is a problem of induction. Right? And so he said it very famously, no matter how many instances of white swans we might have observed, this does not justify the conclusion that all swans are white. And so what Popper advocates that what you should do is you should formulate a scientific hypothesis. And in his view, a scientific hypothesis is valid only if it can be tested experimentally. And then you should collect data to test the predictions. And you should keep your scientific hypothesis until it's disproven by experiments and so on. So you keep gravity, the theory of gravity, until it becomes untenable. Now this view, at about the same time, was operationalized completely by R.A. Fisher, who essentially independently proposed a way of making it very concrete. And so he wrote a very, very important book called The Design of Experiments. And roughly in this book, what does he say? He says, well, suppose you have a hypothesis, and in his charming style, well, this would be a lady tasting tea. And the hypothesis is that there is a lady, and she can, by tasting a cup of tea, she can decide whether the milk or the tea has been added first. And Fisher says that's a scientific hypothesis that can be tested empirically. And so he formulates the notion of the null hypothesis. Right? And the null hypothesis in this case, well, I think it's all rubbish. I think that she doesn't have these extrasensorial capabilities. And so what you do then is you design an experiment to test this hypothesis, and introduces in the process the concept of p-value, which is essentially a measure of how well or how much the data refutes the standing hypothesis. Now, I assume people are familiar with the concept of a p-value, but if this is not true, can you please raise your hand? All right. Okay, so everybody knows what's a p-value. That's great. So Abbas said, you're well educated in Michigan, and I concur. All right. All right, so the p-value is a I see. Well, you're probably not from Michigan. You see, I solved the induction problem already. Okay. All right, so we know what our p-values roughly, and for those of you who don't, it's the probability of observing in the data a discrepancy from what is expected under the standing hypothesis. So you expect a certain noise distribution if your hypothesis outcome of distribution, and if you're over here, you'll have a very low p-values because that's not what your theory predicts. Like if you're over here, you'd expect that if your theory predicts, you will fall somewhere here, but if you're here over here, then it would be evidenced against a standing null. That's the way we used to do science, and that has served us very well. In fact, entering this building, I saw the Salk experiment, which exactly followed this protocol. You have a vaccine, you think it's good, you design a random experiment, you sit. But what has changed? Well, what has changed is that now we live in the big data era and that we have a new scientific paradigm where we have reversed these two things. We collect data first and then we ask questions. Fisher asked questions and then collected data to answer the question. But now we collect data and we ask questions. And so we have large data sets that are available prior to the formulation of hypotheses. And so what we need is we need to somehow reliably quantify what is obtained when you go through this large number of hypotheses and you perform what I want to call data snooping. And it's very different from the kind of science the greats had in mind. It's very, very different. Now, statistics is still extremely relevant, even though we're sort of in a new paradigm, is still extremely relevant because it's a language that lets you understand how you can account for look everywhere effects, and so to understand reliably your discovery in the context of everything that you've explored at once. So why is it that most discovery may be false? Now, there are many reasons. You know, there's fraud, there's incompetence, there's a lot of things. There's publication bias. And of course, we can't solve them all. But there's one reason connected to the big data world where most discoveries may be false, and that was kind of interestingly pointed out by a medical doctor as early as 1989. And what he had in mind is something like this. Let's say you have 1,000 hypotheses to test. But you know, like now, I've been to conferences where people tell me that they have designed robots to generate scientific hypotheses. So they're interested in billions of things generated by a robot. Like how many of these billion things you think are going to be extremely relevant? 5, 6, 7? So we have a lot of hypotheses to test, knowing full well that, you know, out of this sea of stuff we're looking at, because we can, you know, I may understand, I have 300,000 genetic variations, and I'm interested in a response, let's say, whether I have a certain type of disease or not. Well, these 300,000 variations not all of them have something to do with my disease status. So there's only a few that do, and so these are really pictured by this kind of yellow squares, and there are few here. There are 100 potential things awaiting discovery, and so we're going to put them in a corner, and here they are. And what we're going to do is then, suppose we go by the time-honored statistical testing procedures that was given to us by the greats, where we're going to test things at the 5% level. So what does it mean to test things at the 5% level? It means that your chance of making a false discovery is 5% for each false discovery. And let's say that we're in a setup where the power is 80%. Now, what is it? The power in statistical parlance, the power is the probability that you detect an effect when it's there. So in this example, your chance of detecting something interesting when it's there is 80%. So suppose we test things at the 5% level so that the power is 80%. Well, there are 100 things awaiting discoveries, and so we're going to get roughly 80 of them. And I think they are indicated in green. These are my true positives. The yellows are the true things that I did not discover. They are the false negatives. But the thing is that 5% of what is null, what statisticians call null, is also being discovered. And it's 5% of a large number. It's 5% of 900 and 900. So about 45 things I'm going to report cannot be replicated. And so if I actually bunch together this, the true positive and the false positive, we can see that in this example, roughly, well, a bit more than a third of what I'm reporting is actually false. Now, what happens is in a lot of these studies, we're in prospective modes, and so the power is actually not 80%. It's much lower. It's 30%, for example, or even 30%, I'm generous. And so, well, if the power is 30%, that is, well, your chance of finding a true effect when it's there is only 30%. It's not 80% anymore. Well, the number of red things does not change, but the number of green things changes because it's 30%. So now instead of discovering 80, I discover 30. And now I report this, and now my false discovery rate is 60%. 60% of what I claim cannot be replicated. Now you'd say 30%, Emmanuel, you're crazy. Well, not quite. Because if you look at a lot of the fields, like for example, here is a meta-analysis performed by this colleague of mine, John Ioannidis, surveying all fields of neuroscience. These are thousands and thousands of studies being compiled in a single graph. Here's what he found is that, the power in the histogram in power and the median power is roughly 20%. So we are in very low-powered situations. And it's not surprising that a lot of things that is being claimed in neuroscience, it's difficult to replicate, very difficult. Now, statisticians have understood this well, and so they are actively engaged in trying to resolve some of these problems to kind of help address some of these problems. And I'll mention one thing which is quite dear to my heart. It's a false discovery rate theory of Benjamin E. Hochberg from 1995, which may be the most significant achievement in our field in the last 20 years. And so here is what they advocate. They'd say, well, you are testing a large number of hypotheses, scientific hypotheses, n of them, and we can think, here we really think nowadays, we'll see a lot of examples later on, but think the number of things you're interested in testing in the hundreds of thousands. And so what we would like to do is there's a natural quantity what we'd like to control. That is, we would like to control what they call the false discovery rate. And what the false discovery rate is, it is the expected fraction of the number of false discoveries over the number of discoveries. Right? It's an expected fraction of the things that cannot be replicated over the number of things you can report. This method is kind of this concept is beginning to be widely used, not as much as it should, but it has quite of an influence on medical research. And what's great about this paradigm, it's very intuitive. So if I set the FDR to be 10%, what I want that roughly on average 10% of what I claim I make an error, right? And that's fine, because what we're saying is, well, if we want to pursue science, sometimes we have to follow false leads. And that's part of the scientific process. Now, what is their method to actually achieve FDR control, provided that we have statistics for each of these hypotheses that are independent? Well, since you're so good at p-values, I'm going to look at this on the p-value scale. So what you're going to do is you're going to range your scientific hypothesis from the most promising to the least promising. And so what that means is that you're going to take your p-values and you're going to sort them in ascending order. And so here they are. They're plotted over here, and I have 100 of them. And what we have on the left are the smallest. So this is the hypothesis you'd like to reject. The data seems to be strong against this hypothesis. And these are the guys that look to be fairly happy under the null. And what the method is, it's extremely simple. You draw a line, and the line is I, Q over N. So I is the index, Q is your FDR target, let's say 0.1, 10%, and N is the number of things you're testing. And so you draw this line, and what you do is you look at the last time this kind of process, this sort of empirical process of p-values crosses this line. And that's your cutoff. And what you report is you report all the hypotheses with a p-value less than this cutoff. So all these red guys, you reject. You say, that, I believe, is significant. And all the black guys above the last crossing, you say, this are, I prefer not. I think they are nulls. What's actually quite wonderful about this method is it's adaptive in the sense that the cutoff depends on the kind of p-values you get. So if you're in a discovery-rich environment that is a lot of small p-values, then you can see that your process might do something like this. Then the cutoff will occur earlier, and so you discover more. Okay, so the level of significance is adaptive, adapts itself to the kind of process you get. And what they've shown in their wonderful paper is that this very, very simple method, which you can visualize graphically extremely well, will control the false discovery rate. So if you were to follow this protocol, then you would not have the problems that we're discussing here, and everywhere in science. Okay, now of course, I don't mean to imply that Benjamin and Hochberg were the first to think about the multiple comparison problems, but I think they have such a fresh take on it that we should give them a lot of credit for the development of the new way of thinking about multiple comparisons. All right, so the FDR is a sort of perhaps people are used to the type 1 error. And so the type 1 error is the probability of making a mistake. But you see, what's very interesting about the FDR, it's the probability of making a mistake, which is not average over the number of things I'm looking, but average over the number of things that I'm telling you about. And that's the selective inference property. And what we want in statistics these days is that I'm going to look at data, because that's what I do. I look at data, and then I tell you something interesting. And what I want is that the stuff I tell you holds over what I'm telling you, if you see what I'm saying. It's like what I want is like I want the original property of inference to hold over the selected sets. That is, over the selected effects or the selected parameters that I will tell you about after I looked at the data, not before. Now you'd say, okay, this is a new take on multiple comparisons, but what I'm going to try to convince you about is that no, it's not. I mean, it's really a new way of thinking about it, because we can have the same problem with confidence intervals. You know, if you open Science and Nature and all these things, somehow p-values have a bad rep these days, and people think that you do better science if you do confidence intervals. Okay, that's a mystery to me, but that's the way it is. And so you'd see people report confidence intervals. But what we all know, a confidence interval, I think we're well educated. In a large number of 95% confidence intervals, well, what we know is 95% of them contain the population parameter, obviously. Well, that's the definition of a confidence interval. But it would be wrong to imagine that the same rule also applies to a large number of 95% interesting confidence intervals. Right? So here's an example. I have 20 parameters in this, right? And I construct confidence interval for all of them. But now I'm going to look at them for those that do not cover 0, because I believe that there is an effect. It does not cover 0. And so when I look at, first of all of them, well, I have, if I build 90% confidence interval, I have what I want, which is that, well, 17 out of 20 do cover their parameters. So classical statistics works. But if I select interesting things, for example, confidence intervals that do not contain 0, because they seem to be indicating a departure from a null, then this ratio drops to 1/4. And so, of course, this will fail when you replicate. Okay? And of course, what you're suffering here is from the winner's curse. You pick the winners, you pick the rookie of the year, and the rookie of the year will not do as well next year, not because he's less talented, but because he got lucky the first time. Now, ignoring multiplicity of intervals is more common in science than ignoring multiplicity of tests. Now, we could have a blast because I could show you so many things like this. Spaghetti sauce and pizza fight cancer. Last year, I saw an article in the New England Journal of Medicine, like if you eat a lot of chocolates, you're more likely to get a Nobel Prize. Well, that's good for me because unfortunately, I eat too much chocolate. There's a lot of stuff like this that gets reported, and it's because people ignore these multiple things. And so, in response, what statisticians do is they say, well, what you do is you collect data about parameters of interest, effect sizes, if you will, of various drugs and so on. Then you look at the data, you select a subset of parameters, and if you believe what I'm saying, the property of inference you would like to hold is not that, yeah, for parameters that have been specified ahead of time, things work. No, for things that you have selected, you want it to work. And so there's this notion, which is a bit analogous to the false discovery rate, which is a false coverage rate, which says that you would like that the expected fraction of confidence intervals that do not cover over those average over the selection after looking at the data obeys a 95% whatever. Okay. So what is a summary of this first part? This consequence of the new scientific paradigm is that there's a textbook practice on one side, and the textbook is that you choose a model, you choose a statistical model, you collect data, and then you perform inference. What happens in the world is not this. What happens in the world is you collect data, you look at the data to choose a model, and then you perform inference. It's surprising to see that when I look at almost all stats textbooks, and I would love to be proven wrong, that people, all textbooks I know of, ignore the selection issues. Like, okay, so we have textbooks in stats. Do we have statisticians in the room or a few? Okay. So I'm going to find a good model by CP, and I'm going to give you confidence interval for the beta, the coefficients, when the model has been heavily selected. That makes, as if I did not perform selection. That makes absolutely no sense. And we cannot go on like this. Okay, so there's a subset of us. We're working hard on this, and that's what I'd like to tell you a little bit about. What is it that we're doing when we think about this problem? So in the last 20 minutes or 25 minutes, I'll talk about some new work, which we call the knockoff filter. And it's exactly, to me, what I consider to be the most fundamental problem in big data science, which is I have a response, y, like whether I have a disease or not. I have lots of variables, for example, SNP information. I'd like to know which of these SNPs influence this response. Now, I'm very interested in this, and a lot of people are interested in this. Before I get started, here's a young woman, Rena Fogel-Barber. I believe she's as smart as Claude Shannon. And so this is joint work with her, and she's a phenomenal young statistician. And then at the end, if time allows, I'll present some new work with Lucas Jensen, Jinqi Liu, and Yingying Fan. Okay, so the problem I was telling you about is, here's a problem that lots and lots of people study. I'd like to find those locations on the genome that influence a trait. For example, cholesterol level. All right, so we'd like to know which genetic variants have something to do with my LDL level, or with a form of cancer, or whatever. But let's focus on LDL. So what people will do is they will do something like this. They will try to understand, to predict LDL from genetic information. And so what they'll do is they will create a vector of response, which will be cholesterol levels of various patients in your study. They will have variables, predicting variables, which we're going to call X, which in this case might be a genotype matrix. And this genotype matrix might count the number of the minor allele that you have at a given location on the genome. And then they will try to predict the response from this genetic information. And of course, they're going to use models. So models that are heavily used would be linear models. And so I'm going to try to understand why, as a linear combination of this SNP information, and then, of course, I don't believe it, so I have a z, which, if you're cynical, you'd say, well, it's just y minus x beta. If you're less cynical, you'd call this an environmental factor, since that cannot be predicted by genetics. For example, what you eat. And all right, and so they would use something like this, which is the lasso, the least squares of the 21st century, where what you would do is you minimize the residual sum of squares, so you try to get a good fit, enforcing some form of sparsity on the coefficients by means of the L1 norm. Now, I have a second thing. Al, do they know about the lasso?
I would say some do, probably not all.
No, okay. So for some of you, that might be a bit strange. So what you do, I think everybody is familiar with this, is the residual sum of squares. But you're going to regularize the residual sum of squares by an L1 norm that will force the fitted coefficients to be extremely sparse with a few non-zeros. Now, one thing you could do is, if lambda is 0, then what is this? Least squares. Now, can I perform least squares in these studies? Not really, because I have 5,000 people and 300,000 SNPs. So I have a data matrix, if you win, which is fat, which is non-invertible. So I would do least squares. I would get garbage. In fact, the least squares estimate is not even defined. If lambda is infinity, what do I get? 0. And so as lambda goes from infinity to 0, as you'll see, you'll start selecting things. You'll start to include variables in your model. So think about this as a scale, where if you start at infinity, there's nobody in your model, and you decrease this scale, things start to come in. And what people would do, and you see this in a lot of papers, well, they would say, I would fit the lasso because I know it's going to produce a sparse solution. And come on, if you're not 0, you must be significant. So I'm going to report you. Well, what evidence do I have that you're significant? All right, so this is a problem we're going to look at for like 20 minutes, the problem of control variable selection, where we have this linear model. There's lots of things, lots of variables I'd like to know whether they're in the model or they're not. Does the cholesterol level depend on a given SNP, yes or no? And the goal is going to be to select a set of features, xj, or a set of SNP, for example, in this example, that are likely to be relevant. Controlling the metric that Benjamini and Hochberg gave us, the false discovery rate, where I want the expected number of the false positives over the features selected to be controlled. That is, when I go to the biologist and I say, look, I think this SNP has something to do with your disease, then she would not waste more than 10% over time. So why is this a hard problem? It's a hard problem because, let's go back to the lasso example. So it's a simulated data set where I have 1,500 patients in my study and not that many covariates, 500. And what I'm doing is I'm fitting the lasso model. So I'm fitting this kind of regularized least squares estimate, regularized by L1, with lambda equals 1.75. Okay, and so I have 500 variables, 500 coefficients to fit. And these are as a result. And I can see that the lasso does what it's supposed to do. A lot of them are exactly equal to 0, and some of them are not. Should I go and report them? Well, is this a false positive? Is this a true positive? Like, how do I know? Well, in fact, in this case, I do know because I generated the data set myself. So, well, the green points in the example, they happen to be true positives. The black points are false positives. So if I actually were to report these last two discoveries, which is sort of, again, what a lot of people do at the moment, the false discovery rate would be 50%. That is, half of what I'm claiming is false. Now, how do I know this? Well, I know this because I know the grand truth, but in reality, I don't know the grand truth. So how do I answer questions like this? Is this, okay, it's non-zero, but is it big enough to be significant? Well, to answer questions like this, I would need to know something about the sampling distribution of this statistical estimate under the null. Well, that's a crime of the 21st century. I don't know how you get sampling distribution of lasso estimates. And even if you could, it would depend on all the other coefficients, which I have no idea what they are. And so how am I going to get out of this? Right, so we try to estimate the FDP. We would need to get the sampling distribution of lasso estimates. I say just forget it. I don't know how it can be done. Okay, so here comes knockoff. Okay, so for those of you who are not born in the US, a knockoff is a fake. It's the best definition I got was from thesaurize.com. So you see my sources. It's not a name brand bag, it's just a cheap knockoff. Okay, and so the method, what it's going to do, it's going to inject poison in the system. That is, for each SNP that you give me, I'm going to construct a fake SNP. A SNP that has nothing to do with reality. It's going to be constructed by my laptop. And I'm going to use these fake variables as a control group. You're going to have to show me that you're more significant than your fake for me to be, for you to pass a significance threshold. Okay. All right, so we're going to do a little bit of math, but not a whole lot. Okay, so I'm going to build knockoff features, xj. And so I have these true variables. And what I'm going to ask is that these fake variables obey two properties. These knockoffs obey two properties. The first property is that their correlations is the same as the correlation of the original features. Okay, so they have the same correlation structure. And that's captured by this first equation. Right? They have the same correlation. It's a set of variables that have exactly the same correlation. And the second is a bit newer to you probably, is that what I'm going to do is I'm going to ask that a fake variable for SNP number j has a correlation with a true SNP, which is exactly the same as the true SNP as pairs of true SNPs. That is, pictorially is represented like this. It says, you know, I've got this fake variable. This is a true SNP. This is another true SNP. But the correlation between fake stuff and the truth is the same as being as this thing. Okay. So that's the only. Now you say, well, how do you do this? You do this by matrix computations optimization, and you don't go back to the lab. You don't measure new things. You just use your laptop. And what's important about this is these variables that obey these things, they did not ask me to show you your y, your response, the stuff I'm trying to predict or understand. Okay. So we have these variables. And now why are they built this way? Well, they build this way, and I guess that's my conceptual slide. I think we will not see anything more conceptual than this. And it's something like this. Suppose I want to use a simple test. I want to just going to use marginal correlation. What's the strength of the correlation between the variable you care about and the response? Well, suppose my model, my feature xj is not in the model. It's a null feature. Y does not depend on xj. Okay, so I can calculate the correlation between variable j and the response. And of course, it's the correlation between xj and the mean plus xj and the noise. But the way we set up knockoffs, if the variable j is not in the model, because of this property, then xj correlate with the mean exactly like as a knockoff because all the intercorrelations are preserved. So this is preserved, so the mean is preserved. And because I respected the correlation structure, this was Gaussian noise, this is new Gaussian noise with a new correlation matrix, but that correlation matrix has now changed because my knockoffs are faithful to the original correlations. And so what I discover at the end of this process is that when I look at a marginal correlation between xj and y, it's distributed exactly like the correlation between a fake and y. It would not be true if I were to use a permutation method. Because if I were to use a permutation method, that would be fine, but that term would be completely off. And so permutation methods dramatically fail at controlling the false discovery rate. But what that's saying is that roughly, if I'm a null feature, then I've arranged all my variables in a data matrix. This is a J, it's null. And if it's null, whether I'm looking at this variable or this one, it doesn't matter from the point of view of the response y, of what I'm interested in. It doesn't matter. It's just distributed in exactly the same way. Now, what is true for one variable is true for many. So pairwise, all the noise variables, you can swap them and the statistics would not change. All right, now that we have seen this, I can try to give you, okay, and so this is captured by this lemma, which is that what I can do is I can swap any number of nulls, and then when I look at correlations, nothing changes, in distribution, obviously. Of course, at the level of the sample, things just get swapped. That's okay. But the distribution is unchanged. So we have what probabilities call exchangeability of the nulls. Okay, so now I want to kind of show you the knockoff spirits in low dimension, and then maybe we'll operationalize this a bit. But here's my view of how we should do variable selection. What you do is you give me a design. You went to the lab. You give me a design X. What I do is I create my knockoffs. And now I run the lasso on both the original and the fake variables, because I'm going to use them as controls. And so we're going to use x wiggle j as a control group for xj. So now when I run this lasso, it's exactly the same data set as before. It's exactly the same data set as this one. You know, the one where we discovered 55 things and 26 were not good, or 47, or forgot. Okay, it's right there, 55, and then okay. So I get slightly different lasso estimates, and now I get coefficients for both the true variables and the fake. And now if you follow a bit what I'm saying, is that these statistics, they're exchangeable with the nulls over here. So by actually counting how many variables the lasso picks, it's probably a very good guess for the number of nulls that he has picked over here. And so let's go through this. When I run the lasso exactly the same data set with the same value of the regularization parameters, the lasso selects 49 original features and 24 knockoffs. And if you sort of follow what I'm saying, what it says immediately is that there are probably 24 false positives about this. And so if I were to report these 49 things, I could estimate the false discovery rate to be roughly 24.49, which is exactly, in this case, this 47% we've seen before. So I have extraordinarily precise estimates of the false discovery rate. Okay, okay? So that, if you understand this, I think I can just shut up now. Well, we're going to operationalize it a bit. So now we want to see who is in and who is not. And so what you do is you're going to build statistics. And so being in a department that is a bit lasso-centric, we're going to build them on the lasso, but you could build them any way you like. So I'm going to look at the first time a variable shows up on the lasso path, and the first time the knockoff variable shows on the lasso path. Right? And so what we've seen that these things should be exchangeable. If you're null, they should be exchangeable. Okay. And so I've got this thing. So I look at, you know, I'm computing my lasso path. So I start like cos lambda infinity. Nobody is included. And then I decrease lambda. And then somebody will show up. And when somebody shows up, I record, is it original or is it a fake? And I record its label. So I see, you know, here the SNP will, or its knockoff will show up first, and then the SNP or knockoff number 143, blah, blah, blah. I make discoveries this way. You see, I make discoveries. And my statistics is very simple. It's going to be the first time something shows up, and I'm going to tag it. I'm going to say it's plus this thing if the true variable comes before its knockoff, or it's minus if it comes after. And so when W, which is a feature important statistics for a variable, is big and positive, it means two things. It means it occurs early, so it's probably there, and it occurs before its knockoff. Of course, if W is negative, you don't want that variable because the data analysis prefers to pick a fake variable, something that's been generated on my computer with no respect to any physics or biology whatsoever, and so you would not pick it. All right, so now this knockoff selection is very simple. So we're going to go this, we're going to do this. And so we look at the first variable I selected. Boom, that's a true variable. That's this $100 bill. We look at the second one, it's a true variable. Look at the third, it's a true variable. True variable. So we discover original variables. And then something happens, and a knockoff shows up. And then what it shows me, if you're following me, is like how many fake null discoveries there are over here. Maybe one. And I continue. And when I continue is I continue until the ratio between the fake and the number of selections, because I'm going to report this, is below 10%. The last time that happens, I stop, and I give you this. And if I did things correctly, I should be in business. Now, of course, for those of you who are super smart here, there's a stopping time. You know, you waited until something happens. Yeah, things are extremely tricky. I agree. But if you do this way, so we can maybe forget about the math. If we do this way, then it's kind of remarkable that this happens. There's a theorem by myself and Rina that would say that if I implement this strategy, then it controls the false discovery rate. That is the number of false expected fraction, exactly what you want, the number of false discovery over the number of rejection is controlled at level Q. This result is non-asymptotic. It holds no matter the sample size, no matter the noise level. In fact, I never ask you what sigma or the noise level was. It always works. And so it's non-asymptotic, works no matter the design for any noise level, period. Okay. Now, the larger knockoff picture is something like this, where what you're doing really, if you think about what I'm doing, so let's eliminate the first property. Let's look at the second, which is the one I care about. This method would work with any statistics you can imagine or invent that would have the same property. The same property, that when you take a true variable and you exchange it with its knockoff, you just change the sign of the statistic. That's it. Right. So if I swap the sign, if I swap a true variable and a fake, then all I'm doing is I'm changing the sign. Anything with this property is amenable to this analysis. And the immediate consequence of this is that the sign of a null WJ, of an impertinent statistic, the stuff you're going to use to make your decision, if you're null, it's an IID coin flip sequence. So in a way, you can think about them as 1-bit p-values. Okay, so a lot of statisticians are familiar with permutation methods. And permutation methods, what they will do is they will break the association between the response and the variable by randomly permuting people, by putting Michelle's DNA in front of my LDL. And she doesn't want my LDL level, I can tell you that. And so what you do is you permute rows at random to break the association between the response and the variables. When you do this, you don't do something which is equivalent to knockoff, because by the central limit theorem, your new variables obtained by permutation are decorrelated from the truth, from the original ones. And so if we repeat the same experiment we've done, if I fit the lasso pass, and here I have the true signals, here I have the null signals, the things that I should not include, and these are the coefficients for the permuted features, we can see with our own eyes that the distribution of this is in no way representative of the distribution. So if I were to use this as control, I would be completely toast. And of course, that's what you show is if you use knockoffs built by some permutation method, that is a total catastrophe at controlling the false discovery because it ignores correlations between variables. Okay, so this method works well, and all right, so it has power, it works well, it controls the FDR, that's the theorem. Okay, maybe 3 minutes. Here's an interesting data set which is curated by my colleague from Stanford, Warren Schaefer, who works in the medical school. So we were interested in HIV drug resistance. So you have several types of drugs. And so you have different drug types. You have different number of drugs per type. And you have people in your study. And what is known is that there are certain mutations that are associated with a log-fold increase of lab-tested drug resistance. So we'd like to understand which mutations make drugs ineffective. That's the thing. Now, I don't know the ground truth for this stuff. But I can apply the knockoff methods on this data set. And so here's the first type of drug. So we have 6 drugs in the first type. But the reason we chose this data set is that it's well curated. And also, in the past, people have performed what we call longitudinal studies, where they have followed people, so they have ideas of what mutations increase drug resistance. based on a cohort that has been followed through the years, an independent data set, so to speak. And so what we can do is we can use this knockoff method to try to find those mutations that seem to be associated with drug resistance and compare its findings with what's available elsewhere. Now, so there's this TSM panel list, and in the example for these drugs, there are about 37 mutations that have found to be, over the course of many years and many patients, to may have some effects on drug resistance. Now, we use a knockoff, and so we're going to focus on, let's say, this drug, NFV. And in this example, knockoff makes not 37 discovery, it makes 29 or 30, I don't know what that number is. And the blue region is a region that exists somewhere else. The orange region are knockoff discoveries that are not in this TSM list. And so what we see, no matter what plot we're looking at, is that there's a lot of blue, meaning it finds stuff with previously known associations, or we believe that they are true associations, and a little of orange indicating this false discovery rate proportion. And so it's gearing up towards false discoveries, and we control, and so we've analyzed a lot of data this way. This is other types of drugs. And you can see here, for example, that knockoffs would make a lot of discoveries, almost as many as on the TSM list, with very, very few things that have not been reported before. Okay, so I wanted to show you some extensions of knockoff, but maybe not this time. Huh? All right, so maybe I'll say just in my concluding slide, what the knockoff filter is a precise inference machine that lets you design the statistics any way you like. And then you go through this machine of building knockoffs and applying this knockoff filter. And of course, if you have good statistics, you have lots of power. If you have bad statistics, you have little power. But you can build knockoff, you can design statistics, and then this machine will take care of inference for you. Now, I've presented the theory in the linear model, but we have extended it recently, and it's in the slides I skipped, to any non-parametric model you can think of. And so that I did not have a chance. But just to go back to the theme of this lecture, it is true that we have to be extremely worried about the irreproducibility of scientific research, the fact that science does not self-correct. What I want to tell you is that a lot of statisticians are extraordinarily engaged in working on these extremely important problems. There's a lot of activity. We need many more people to help us. And with this, I'd like to thank you.
So his idea was that he would wheel this thing around, and it would eliminate most of the functions that surveyors performed. And he tried really hard to make a commercial success of this invention and fell short.